So since these power series are in fact polynomial series, we can differentiate and integrate these very easily just using our power rule. So what does differentiating, integrating power series actually do? Well, we can actually generate new functions by starting with some basic functions and differentiating and integrating these functions into new functions. So if you take a look at the basic power series, this is our infinite geometric series, so it's equal to this, this SA over 1 minus R formula, or in this case, since we're starting with 1 over 1 minus X, where X is our common ratio. And we can do a substitution, and we did this in some exercises before. We can substitute negative X and embed that function as a composite function into our original function here, and we're going to end up with 1 over 1 plus x squared. And this happens to be the derivative of the arctan of x. So if this is the derivative arctan of x, we can, we have basically a series that represents the arctan of x, which is essentially when we substitute the negative x squared into our basic power series, we're going to get this function here. So we get this alternating power, every second power series here. And this series just represents, this basic 1 over 1 plus x squared, which also means that this must be the derivative function of arctan in its, infinite polynomial form. Well, we can generate the arctan function as an infinite series by taking that function and integrating, because we know that if we integrate this expression here, we're going to generate the arctan function. Well, if that's true, well, we can replace this. Remember that the infinite series is essentially this function. And we can integrate that, and we can integrate this function to say, well, we can integrate this expression here, right? If we integrate this series, we're essentially integrating every term of that sequence, which then means that we're integrating all these pieces, and we're just integrating this general expression then. So our arctan function, our infinite series for arctan then, as we integrate this, well, we're going to increase the power by 1, yet x to the power 2m plus 1. We're going to divide by that new power 2m plus 1, and that's going to be the integral of this function here, okay, which is represented by this polynomial. So this new series must be the infinite series that calculates the arctan function. The arctan function looks like this. If I want to draw the arctan function, I can just use this infinite series, x minus x cubed over 3 plus x5 over 5, etc. And this function now is a power series for arctan. So we've now generated a power series for arctan, but furthermore, this function is a polynomial function, so it's continuous and differentiable within the radius of convergence. In this case here, since it's an alternating series, we can actually show that it has an infinite radius of convergence, so it converges for all real values of x. So differentiating and integrating these series, we can generate new functions, okay? And we can generate power series for these functions. So these are very useful to us. We can actually now start finding new ways to generate new functions and these infinite series functions, which are very useful to be able to calculate things. So if we want to put them into computers that do add, subtract, times, and divide, well, now these functions can now be applied in real world contexts. So what we're going to do is we're going to start with a series of sine function and generate it to get a cosine function. Okay, so we can do this for all sorts of functions.